All right, what we want to do here is we kind of want to talk about why mean, median, and mode would be applicable to data. We can describe a data set with these three entries. Um, the mean takes into account every piece of data, but if there is an outlier or a data entry that is not close to the other data entries, it can skew the value of the mean. So here's an example of some ages, and notice that 65 is not near the clustering of these other ages. And so if we're to calculate the mean for this data, add up all of the individual data sets and divide by the 20 pieces of data in it, the average is 23.8 years, but the median is 21.5. The most occurring entry is 20, or the mode. So we have these three descriptions, mean, median, and mode. And let's see what happens with the different pieces of data. So the mean takes every entry into account, but that 65 is pulling the mean away, where it's pulling the mean really past the bulk of the data because its value is high. The median takes every entry into account and is not really affected by the outlier as much as it sits in the middle of the data itself. And the 21.5 with the cluster of 22s, the cluster of 23s, right? If we come back up to the data here, right, we look at the median 21.5 in here, and we see this cluster of 20s and 21s and this cluster of 22s and 23s trailing off with these 24s. And the only reason we can see this is the data is in order. But the 65 pulls the mean forward. And then there's this huge repetition on 20. So the mode doesn't seem to represent a typical piece of entry. The median seems to be sitting closer to the middle of the data, and the mean seems to be at the end of a cluster. And so if we graph this, this is what we get. We get the outlier here and this gap on it. And then we get the median, which is sitting really in the middle of this chunk of data. We get the mean, which is almost pulled out of the chunk of data. And we get the mode, which is to the left of it. So visually looking at it, it looks like the median is the better description of this piece of data. And that's one of the things we're going to do is we're going to move from visualizing these things and the numerical measure and looking at how we can compare what the numerical measure means to the visualization. Another way that we can see means is a weighted mean. And a weighted mean gets a specific formula here. And again, we're going to go back and forth with our technology on this. But what it says here is that we have the sum of each x value times the weight divided by the total of all the weights. So it's an average, but there is a value that's multiplying the data values, and that value weights it down. And what we want to do is add up all the weights to find the middle. And so what we're going to do here is we're going to look at that with a common data set here. Let me switch over to my Blackboard. And we're going to look at grades as a means of weighting. So we could have someone that had a series of grades across a semester. Now in a grade point a 4.0 grade point scheme, we have this value for the grades. So there's a numerical value. So this is the letter grade. And then we have this thing called credit hours. My pen is not that responsive, and it's making my handwriting look 20 times worse. There we go, increase the sensitivity. So we have credit hours. And so we would hope that a 4-credit course has more weight in the overall score than a 2 or 1 credit course. So that was a 3-credit course, that was a 4-credit course, this was a 1-credit course, and 323. So let's set this into columns of information. So what we'll do is we'll turn the letter grade into points, and we'll let the credit hours be the weight. And so the formula, the overall grade, or the mean grade, is the sum of all the x's times the weight that goes with each x divided by the total weights. Well, that sensitivity is working better. So this is a weight. And so we're going to multiply the piece of data by its weight, repeat this, and add up the weights. So let's turn this into, let's make a neater table out of this. So how many entries do I have? 2, 4, 2, 4, 6. Sorry if my lines are not as evenly spaced. So we'll turn the letter grade to C was a 2.0. And so this will be our x's. The credit hour will be our weight. So 2.0, 4. D was a 1.0. A was a 4.0. C was a 2.0. And B was a 3.0. And then the weights were 3, 4, 1, 3, 2, 3. So what I've done is I've converted the letter grade to a point system and the credit hours to the weights. What our formula is asking, or for what the GPA or the grade point average, is to multiply the score by its weight. So we'll tend to make a column here for x times w. So 3 times 2 is 6, 4 times 2 is 8, 1 times 1 is 1, 4 times 3 is 12, 2 times 2 is 4, and 3 times 3 is 9. So this part here that asks for the sum of the value times its weight is asking us to sum this column that we made. So we can come straight down and we can say 6 plus 8 is 14, 14 plus 1 is 15, 15 plus 12 is 27, 27 plus 4 is 31, and 31 plus 9 is 40. So the sum of the value times the weight is equal to 40. And we need to divide this by the total of the weights. So and that means we sum down this column. So 7, 8, 11, 13, 16. So the sum of the weights is 16. And so this equals 40 divided by 16. Trying to get my calculator here. 16 goes in twice, right? I'll just do it by hand over here. We'll keep, what, 2 decimal places. So twice, 32, 8. So 16 goes into 80 5 times. 5 times 6 is 0. Carry my 3, yeah. So 2.5. And so the average grade point out for a student with this grade record, using the weights, using the fact that a lower credit course doesn't affect the score as much as a higher credit hour course would. And so this is how we do weighted averages. I do weighted averages with the homeworks in a lot of classes. Some homeworks have a different weight than exams in some classes. And it's the same idea. The weight times the value gives me a measure of the overall effect of that category. And then in the total weights is what I need to divide by. So let me see if I can switch back here. Got way too many keys to click here. Another thing we can do is we can actually find the average of a frequency distribution. Remember when we did the frequency distributions, I tried to emphasize, and I hope I did, is that we lose information about the data when we put it into a frequency table. We only see the number of things within a class. We don't know what values go into the class. So this tells us that we can take the midpoint of the class and multiply it by its frequency, and that gives us an approximation of the mean that we could get. So let's use this formula in an example here. Switched over there. All right. So let's take the data that we used from Chapter 1. So let me just pull this up here. Our class midpoints. All right, we had 155 to 190, so it had a midpoint of 172.5, and then we increased by 36. So let me see if I can pull up the data. 244, 280. All right, there were 7 classes in it. Just remember from chapter 2, section 1, we had used this data. It was the screen time, and it was the example we did to make our own frequency distribution. Pull back into your notes and pull that back up, or flip back in the book to it as I get all the data in here. 316, 352.5, and what's the last piece of data? 388.5. So these were the midpoints for each of the classes that I had. Let me give myself some room here. And so when we did this, we put all of the data into the bins and we counted up the frequency we would get from it. Sorry if my boxes are going off a little bit weird here. I just want to get a bit of a table going, because what I want to be able to do is create 2 more columns here. And so we could report what the frequencies were, and it was 325. So our frequency, whoops, that's a line. I want a pen. Sorry if I mumble when I write things here. So 325 6743. and we made a histogram out of this. So if we want to know what the average was for this, we want to sum our frequencies times the midpoint. I'm just going to put a little x sub m there to say that it's the midpoint, because we don't have every piece of data, and we're going to divide it by the total number of samples. And if we remember, our total number of samples was the total number of frequencies, or the total number of frequencies, which in this case was 30. And so notice this really acts like a weighted mean. The weight is the frequency, and the piece of data or the score we use is the midpoint. And then in the sum of all the frequencies is the total number, total set of the data. And so what we need to do is we need to construct the multiplication of the frequency times the midpoint. Now again, this is not the true mean of the sample, because the data might not be centered around the midpoints of each class, but it's a really good approximation because we've lumped everything into these 36 wide, a value of 36 wide bins, so it will be a close approximation. So let's see, 172 times 3 is 517.5. And let's see, 2 times 208.5 is 417. And so we're doing the frequency times the midpoint. So 1222.5. Now we're getting some bigger numbers because we have higher frequencies. And 4 times 352.5 is 1410. And 3 times 388.5 is 1165.5. And so we're going to sum down this column. So we come through and enter all of these into our calculator. And we get 8,631. So the average of our data set would be 8,631 divided by 30. Or if we put it into our calculator, we get 287.7 rounded. That's a lot of calculator use. So guess what I'm going to do with this? We're going to take both of these examples and we're going to use them in Excel. So I'm going to come over here to Excel. And instead of getting rid of my previous example, what I'll do here is I'm going to rename the sheet down in the bottom, example 1. Then I'm going to create a new sheet by hitting this plus sign. And then I'm going to rename this example 2. I'll make this big enough so you can see it. And what we'll do here is we'll do the average grade point at grade points. So we'll do grades, credit hours, and then we'll do grades. Let me do abbreviation. Well, actually I'll use the variables. This was the data value, this was the weight, and so we're going to look at x times w here. So I'll use the formula to put things in. And make sure I'm in the right screen here. Good. All right. And so let's grab the grades that we did and let's look at how we can have Excel turn this into and do our calculations for us. So the grades we have was C, C, D, A, C, B. So that's 221423. So 221423. 4, 2, 3. And the credit hours for those classes were 3, 4, 1, 3, 2, 3. 3, 4, 1, 3, 2, 3. And so what we want is we want to make a column of the grades times the credit hours, or X times W. So what we're going to do is we're going to say equal B3 times C3. And so the times is shift 8. It's the asterisk. And so this will do 2 times 3. But what's nice is Excel lets me click on this little box in the corner and drag it down. And it will update the calculation, changing the cells. So notice I did equals, if I look in the formula bar, B3 times C3. But when I dragged it down, it updated it, so I have B4 times C4 and so on. Now, the two things we needed was we needed the sum of the weights. So I can take equal sum, and I can do C3 to C8. So the sum, C3 colon C8, it highlights the weights, and I get the 16 here. And I can do the same calculation here. I'll do the sum of D3 to D8. And I have the sum of the weight times the data value. And so my GPA average was the weighted sum. So that was these divided by this. So I'm going to take D10 and divide it by C10. And we get the grade point average we got. What's nice about a formula like this, and I used to do this in my classes, is, I'm getting a D in this class. What happens if I raise that D to a C? And so I can change it, and the formula takes care of that. It moves it across. And so that brought me from a 2.5 to a 2.6. Well, let's say this 4-credit class, which is on a C, what if I spent my time trying to get that up to a B instead of trying to improve the 1-credit class? And that actually brings me up to a 2.75. So once we put in a series of formulas, we can change the data values, and the calculations will update for us. And that's a very powerful thing we want to use for us. All right, let's look at example 3. I'll increase the size of this. And this was the midpoints of our frequency diagram. So midpoints, frequency. And again, I'm going to use variables just so you can line it up with the equations. We're going to call our midpoint our X value, and we're going to call our frequency F. And we wanted to know X times F. And so if we go back to the example that we did in section 1 of chapter 2, we did 172.5, 208.5. Let's see if it's recognized what I have here yet. Nope. Oops, Z. What was my next value here? Adding, what was our difference? It was 36, so 244 and 280. Oops, I typed in 208. It should be 208.5. 208.5, 244.5, 280.5. Yeah, and now it recognizes our midpoints. One of the things you can do with Excel is that once you have enough things that are adding by the same, so let me show you what I did here. Our class widths were 36. And so what I did is, well, I'm adding by 36 each time. So if I select all of these and I ask to increase how many I have, Excel's going to recognize that it was adding by 36 and it's going to fill in the rest for me. So once you start adding by a continual amount, especially with class widths, you can select and drag down to have Excel finish. So our three frequencies was what? 325, 3, 2, 5, 6, 7, 4, 3. All right, and this works exactly the same. Right, taking a frequency distribution where you just have the frequencies and the midpoints works the same as a weighted average. So I'm going to say I want to multiply x times f. So I'm going to multiply B3 times C3. But now that I have this, I'm going to drag down my calculations so I don't have to go through and do any other calculations. And then in the sum of my frequency, so I'm going to sum C3 to C9. And I'm going to equal sum D3 to D9. And so equal sum D3 colon D9. And so my mean is equal to D10 divided by C10. And we get an approximate average for a frequency distribution, even though we no longer have the individual pieces of data. And so we're going to want our technology to be our calculator for us when it can be. All right, so distributions will end up having shapes. A symmetric distribution or a roughly symmetric distribution has mirror images. It falls off equally or rises equally in each direction from the middle. And in this case, then the mean, median, and mode will all be the same. So notice on the graph here, the mean, median, and mode are all pointing to the same place. If the distribution is roughly symmetric, then in the mean, median, and mode will line up because the most stuff is in the central column. The central column is the median, and the mean average lies within the central column. And so we call this a symmetric distribution. A uniform distribution has approximately the same number of frequencies. So there will be no mode because all the entries are about the same, but it will be symmetric. So the mean and the median will be in the middle. So this is a uniform distribution. Skewed left talks about the tail of the graph. And if the data has a tail or an elongation out to the left, we're going to say it's skewed to the left. It bulks up on the right. And what happens is the skewing pulls the mean to the left, and the median stays in the middle, while the mode gets pulled to the right. And so we generally say in a skewed left distribution, the median is greater than the mean. I tend to reference by the mean. I'll say the mean is less than the median. Either or, we see that the mean is going left, which means it's smaller in value than the median, and the mode is being pulled to the right, so it's larger value than the median. And of course, we could have a skewed right distribution, which has the tail running off to the right, and the opposite happens. The mean is now greater than the median, and the mode is now less than the median. And so that finishes section 3 here. We'll continue with section 4.